To repeat from last time, what we did last time, we considered how to analyze a complicated antenna. An antenna that is much larger than the wavelength, that has currents flowing everywhere. Say like a Horn antenna fed with a waveguide from a generator. And now with such a complicated antenna, of course, there are currents in many places here. There are currents in the walls of the Horn antenna. There are currents inside the waveguide. And all these actually do contribute to radiation. But we would like to find a simpler solution. And the simpler solution is to consider just this aperture here. So to only consider the radiation from the aperture. This makes sense. And how to calculate the radiation? We introduced the Huygens principle with Huygens sources on this aperture here. Huygens sources that may have an electric field and magnetic field. And these two fields, electric and magnetic field, of course I have to take just the magnitudes of the fields because I cannot divide errors. These are equal to the impedance of free space. So this is mu divided by epsilon, square root of this. And this is approximately 377 ohms. So we approximate this with a wave in free space, that propagates in the direction z here, that E and H are at right angle to each other, and are at right angle to the direction 1z. And of course also E is orthogonal to the direction 1z. And we wanted to calculate if these are H0, E0 on the aperture. If we try to calculate it in the far field, of course, in the far field at the distance r, the field here, E, what is this field like? And this angle here is theta, the polar angle. We found out that this radiated field from such a Huygens source is equal to what? This E is equal. It has a polarization that tracks actually the polarization on the aperture. It is not exactly equal because of spherical geometry, because the unit vectors here change their direction with the position, but it tracks. So if this was vertical, if this was direction 1x here, and theta is small, this one is also 1x. Otherwise, you have to track the direction because polarization always has to be orthogonal to the direction of propagation of the wave. So we should never get any longitudinal component. Okay, there is a physical constant, J over 2 lambda. There is the field on the aperture, E0, without polarization, I write it this way. Delta x, delta y is the size of our Huygens source. We do have radiation, so we have delay, e to the minus jkr delay divided by the distance r. And we have some radiation pattern of the Huygens source. It's not particularly complicated, 1 plus cosine of theta. This is the cardioid radiation pattern. So this was the way to analyze complicated antennas, thinking that here the field in a large aperture is almost a wave in free space. That this thing holds and this thing holds. This is not exactly true. But the larger the aperture, the better the approximation. The larger the aperture, the closer we are to this approximation with the plane wave field in infinite space. So this is not such a bad idea. If we calculate now the directivity in the direction 1z, the directivity, we found out this for the directivity for P over lambda squared. In the numerator we had the field squared, the maximum field squared. So integral over the area A of our aperture, E0 without the vector sign, because we hope that we are in the correct direction. X prime, Y prime, these are the coordinates of the source, dA, and we have the field squared over here. X, Y prime, Y prime. In the direction Z, there is no change in the delay. In the direction Z, in the Fraunhofer region, at the Rayleigh distance, there is no phase to be corrected. While in the denominator, we have integral of the power. Power, not power integrated over infinity, because that's difficult to calculate. It's nothing wrong, but it's just difficult to calculate. Rather, it's much easier to calculate the power flowing through this aperture. And the power flowing through this aperture is proportional to the field squared, Y prime, squared dA. So this was the directivity in the direction 1z. Maximum is in the direction 1z. Most apertures are designed in this way. I should bring next hour an example where this is not true. I should also show you the example where these things do not hold. But our simplification is that we have the maximum in the direction 1z. Of course, this thing simplifies much if the illumination of our aperture, E of x prime, y prime, I may write it as a vector here, this is a constant. If this is constant, then this thing simplifies into what? This thing simplifies into directivity is 4 pi over lambda squared times A. In fact, we defined a few new quantities last time. If we still have radiation in the maximum 1z, but say that the illumination of this aperture of x prime, y prime is not constant. What do we have to do then? Then we can, okay, the formula remains the same as it is up here, the general formula for the directivity, but we will probably get a directivity that is somewhat smaller, so 4 pi over lambda squared, times an effective area, where this effective area, A, where this effective area of the aperture is actually smaller than the real area of the aperture. We can also define an illumination efficiency. That's the ratio between the two. Effective area divided by the real area. We can also try to calculate our illumination efficiency. Our illumination efficiency now, this illumination efficiency should not be confused with radiation efficiency. Radiation efficiency, as we were talking with the Tesla coil, with the half-wave dipole, is related to losses. Actually, we bring some power to the antenna, just a small fraction of that power gets radiated by a Tesla coil, and a large amount of that power is dissipated in the resistance of the wire making up the coil. Well, this is illuminations efficiency. This means just how well are we using this area here. Are we getting the maximum directivity out of it or not? Probably not. Probably this thing will be less or equal to 1. But there is no power lost here. So we still radiate all the power flowing through the aperture because there's no lossy material in between here. This aperture efficiency, just aperture illumination efficiency, just tells us how well are we using the area. But there is no power lost here. So do not confuse both the terms with the efficiency we had before, because there are no losses here. It's free space. We cannot have losses in free space. So this aperture efficiency could be now calculated with our integrals. How? This way. So we have the integral over the aperture of the field, y prime dA, and this is take the absolute value squared, and below we have A times, prefer not to write dots when we don't have vectors, integral over A, and here is the power flowing through the aperture. So field squared dA. Well, here the square is on the outside. So we could also calculate the efficiency, illumination efficiency, how we do this. Now, this was a theory from last time, just repeating things I told already last time. Now, the issue is, how do we make these antennas? How can we make them? Well, it's necessary to have a field that's similar to a plane wave in free space. One of the possible solutions is to have simply a parallel plate line. So have one plate on the top, the other plate on the bottom. We connect the generator to these two plates. The generator. Plates. And what we get here, we have an electric field on the aperture. We have a corresponding magnetic field. And this field looks pretty much a plane wave in free space. So in this way we could generate such a field. And this device here is actually called TEM horn, Transversal Electromagnetic Horn Antenna. Because we could do the same thing, we'll draw it here. Also opening, not just a constant cross section, but an opening section, say, having such a section here, having another plate on the bottom, connecting the generator in between. So here is the generator, supplying these two plates, an opening line, pyramidally opening line, that we have the electric field here, E on the aperture, and we have the corresponding magnetic field. And this should be really called a TEM horn. The TEM horn is a useful antenna, but it is also built, it is frequently used in electromagnetic compatibility testing. So it's something that is used actually. It's not something just pure theory, but it has problems. It has problems making calculations because where do we exactly have, where is exactly our aperture? Our aperture is not just this area here. There is also stray field around. So there are also field lines of the electric fields going around here, or on this side around here. So we don't know what the aperture is, and here calculations may be quite wrong if we don't account for all this stray field. This stray field might also radiate sidewise if I draw the field lines of the electric field. So it's not shielded on both sides. That's the reason why the TEM horn is not particularly popular, though it is used in electromagnetic compatibility testing to generate strong and well-known electric fields. It's a useful antenna. but it's not that popular as an antenna. What we could do, we could use a waveguide horn. And now you are not, unfortunately, you're not all familiar with waveguides. What do we know about waveguides? So, metal waveguide. A metal waveguide, the simplest thing to calculate is a rectangular metal waveguide. Where we have the electric field still in the same direction, aperture here. Just a few words about the coordinate system. We write x-axis here, we write y-axis here, and we have z-axis over here. So that you know where the axes are. And we have the corresponding magnetic field in the y direction. So it's the same as here, exactly the same as here, same situation, for a small difference. The most important difference here is that this is totally defined by the waveguide here. These two side surfaces are metal. So this is all metal. This is a rectangular metal tube. So we may not have here stray fields getting around this, like in the case of the unshielded parallel plate transmission line. How do we explain the operation? Well, we may start from a parallel plate transmission line. From a parallel plate transmission line where we load this parallel plate transmission line with shorts, wire shorts, this way. If these shorts here are a quarter wavelength long, so this is lambda quarter, then a quarter wavelength line is a quarter wavelength transformer that inverts the impedance. Here we have a short. A short after a quarter wavelength is transformed into an open. So these shorts actually have no influence on the transmission of the wave inside this line if we add such shorts. And if we do this, we actually get a rectangular tube. So this rectangular tube here is actually a central section of parallel plate transmission line. And now we have sideways these shorts that all add up into a tube, into a metal tube, so this way. Hope you understand the drawing here. And also make the same on the other side. I will use another color here just to show where is the tube on the other side. Here so this is the other side of the tube, and the other side of the tube is here. So I hope we understand how I came from a parallel plate transmission line to a waveguide. But now this waveguide is loaded. If these things are large enough, if they have at least a quarter wavelength wider, then this thing can work. But it has somewhat different field inside here. The field is somewhat different in such a waveguide. What is the theoretical solution now for the electric field? If we see up here, the solution for the electric field, electric field inside the waveguide, is direction 1x. It's a constant depending on the power of our generator. It's a cosine of pi over a times x, where a is this broad side here, a. B is the narrower side. B over to B, and A we have on the bottom. And we have also the delay. The delay we have e to the minus j beta z, where beta is the phase constant. Of course, where is now our calculation? That this thing now should fit into the Maxwell equation. In order to fit into the Maxwell equations, then we have to, the requirement is pi over a squared plus beta squared is wave number squared, or this is omega times square root of mu 0 epsilon 0. Okay, this is from the electromagnetic side of view. So this solution will solve actually the Maxwell equations, the wave equations, provided that these constants obey this rule. We could calculate the corresponding magnetic field here. What is the magnetic field like? The magnetic field here is now, according to Faraday's law, J over omega me 0, but we know all that we have me 0, curl of E. And now taking this curl, what do we get outside? Well, I can write the curl, I have the time. So I'm just worrying about the time used. The determinant for the cross product, the derivatives over the coordinates, and our electric field only has the x component. So here is 0, here is 0, and I will use another color here just to make the picture nicer. So it's c times cosine pi over x times e to the minus j beta z. Okay, that's the x component. Which components do we get for the magnetic field? There is no x component, of course. There is no component parallel to the electric field. There is a y component because this thing has the derivative over y, and I can write the y component right over here. 1y, we have this component. This derivative is plus, while this derivative is minus. Derivative over z of this thing here in minus j beta. Minus j beta times j is 1. So the constant actually here is our constant times beta, because minus j cancels with j, omega me. Times what? Times cosine pi over a y. Y, this is y. Oh, I made a mistake here. Oh. This is a function of y. Already here I made a mistake. Y. Here. I have to correct this. Oh, y. The field changes the direction. I will draw the sketch. I make the sketch. Upper here. E to the minus j beta z. This stays as this was. And we also have a z component. A z component that's okay, we have no derivative over x, but we have minus derivative here. Minus derivative here, and derivating cosine, it's minus sine. So it's minus sine, and the minus sign of the determinant gives a plus sign out. So we have plus 1 z. Here we have c times pi over a. Yes, we have this j here is still left. J is still left. J is still left. Omega mu. And we have the sine function of p over a y. Before I made a mistake, I wrote x. E to the minus j beta z. Just thinking about the power flow, the Poynting vector. This is actually real power, so this is active. While the z component is imaginary. This will be reactive power. Reactive power. When I multiply, so this was on the aperture H0. I should write H0. Okay. Forgot this. So these two multiplied will give a real Poynting vector, a real power flow in the direction 1x times 1y is 1z. The real power flow that flows, so the real power of will be in this direction, the real part of the Poynting vector, okay? And this one times 1x times 1z will give something in the direction 1y. So the imaginary power is going to oscillate from side to side. So in this direction here, this will be the imaginary part of S. So of course, if I added such a support structure, this support structure is resonant. This will hold some energy, both oscillating between magnetic energy and electric energy, but this energy is going to oscillate sidewise in our waveguide. So just to explain what is going on. How much are these terms important? If I raise the frequency, I raise k, this term stays constant while this term is growing. Beta is growing while pi over alpha is constant because pi over alpha is defined by the dimensions of our waveguide. So while increasing the frequency, this term stays constant while this is growing because beta is growing over here. So the higher the frequency, the more important the real part, the less important the imaginary part. So our assumption that we have had here a plane wave that just has a real Poynting vector is completely makes sense because this will become less and less important as the size of our waveguide is growing. So we will really have also this beta, if omega goes to very large values, this beta becomes equal to k. So if, just to explain, so if omega goes towards infinity, towards high frequencies, then beta is going towards k. Makes sense. And we will have an almost plane wave. But the real aperture we have here, our real aperture, I will redraw the aperture once again here. The real aperture that has sides, the longer side I, the shorter side B. The real aperture will now have a cosine distribution. So we'll have the strongest field in the center of our waveguide, and this field slowly decaying to the edges of our waveguide. So this field is decaying towards the edges of the waveguide, but is strongest in the center. But if the frequency is large enough, it will be a cosine distribution, but it will be a cosine distribution, but the ratio between E and H will be almost zero, will be almost plane wave. So all our assumptions for this formula hold very well, as long as the frequency is large enough, not right at the cutoff of the waveguide. So what do we do now? We can calculate the directivity of our antenna, okay? Or the radiation efficiency. No radiation efficiency, sorry. Now I made the mistake I thought before. The illumination efficiency. The radiation efficiency is something else. The radiation efficiency here is almost 100%. Always, because we have no loss in the free space. So let's try to calculate now what the directivity is. Or maybe go immediately to the illumination efficiency, what the illumination efficiency here is. The illumination efficiency now is what? The illumination efficiency is, on top we have the integral over the whole aperture, E of the aperture, x, y. I may write without primes because it's just hard work to write all those prime signs. dA squared, and at the bottom I have A times integral over A, field squared, squared dA. Now let's see what happens up here. Our aperture A is of course A times B. Not without any sign in between, because these are not vectors. A multiplied by B. So let's see what happens with the integral on top. The integral on top, we have what? We have integral from minus a half to plus a half, from minus b half to plus b half. Okay? We have the electric field is constant times cosine p over a y times e to the minus j beta z. The first integral from plus a to minus y goes over y. So this integral from minus b to plus b goes over x, so it's dx dy, absolute value squared. And in the bottom I have, this is AB area. I have the integral again from minus I half to plus a half, from minus b half to plus b half. And I have the absolute value of C times multiplied by here cosine of p over a y e to the minus j beta z squared. So I could take here dx dy, x dy. What I could do here really, this beta z does not make sense, because on the aperture z is 0. Here it's the origin of our coordinate system is here, and here at the origin z is 0. But nevertheless, this thing cancels out. Even if I was leaving z here and in this complex exponent, it doesn't really change the result. But I should take really z0 because I am on the aperture. So that simplifies my life. So let's see what remains of the integrals. On top, c is a constant, comes in front of the integral. Absolute value squared, so it's c squared, okay? Then, integration over x. X goes from minus b half to plus b half. this is not a function of x. So this is not a function of x, this is just b. Squared is b squared. b is real, so it's just b squared. I need not write the absolute value sign over there. And then I have an integral from minus a half to plus a half. Integral, sorry. Should be integral here. Of what? Of cosine of pi over a y dy, and this should be taken absolute value and squared. In the bottom, what I have ab in the bottom. Then I have an integral over x, and this is not a function of x, this function here. So it's just times b. B here. Then I have the constant squared. Beta z would, the absolute value would eat beta z in the imaginary, the imaginary exponent function of an imaginary argument. So I'm left with the integral from minus a half to plus a half of what? Of cosine squared of p over a y. I would prefer to write here parentheses so we know what the cosine works with dy. Okay? Now let's see what happens out of this thing here. So c squared cancels out. Also b squared cancels out. b and b cancels out. So this thing already simplifies things. So let's rewrite now the illumination efficiency here. What it is, the illumination efficiency. So on top, I have the cosine of pi over a. This is a over pi. A over pi squared. And then I have the integral of the cosine. The integral of the cosine is sine. And this sine goes from minus 1 to plus 1. So this integral is 2 absolute value squared. Okay? So we are here. What do we have in the bottom? In the bottom we have a. We are still left with a. We are left with the integral of cosine squared. This cosine squared is actually integrated over half of its period. If we integrate a cosine over half of its period, cosine squared is cosine squared. Could rewrite this cosine squared. Cosine squared of u is equal to 1/2 plus 1/2 cosine of 2u. This cosine of 2u of twice the argument is now integrated over its whole period. So this gives 0. This gives in the integral gives 0 because we go over the whole period of the cosine 2u. It's just 1/2 left, 1/2 left, but multiplied by what? We have to consider this p over a here, so a over p. A over p over p. Sorry. Not a over p, but we said we take this 1/2 of integral over a. So it's 1/2 of this interval, so it's a half. A half. If we take just this term here for the integral. So now we see what happens here. What happens here? We have now, here we have a squared cancels out. So a squared and a squared cancels out. And we have p squared in the numerator, and we have 8 in the denominator. Okay? And this is approximately 81%. Not so bad. Not that bad. Not that bad. We have an illumination efficiency of an antenna that we really can build that's 81%. This is not that bad. So we used our area, the efficiency of using our area of our waveguide is 81%. The efficiency illuminated, this is not power lost. And in fact, we have such antennas here. We have such antennas. So this rectangular copper tube is a waveguide. This is a flange to connect to other waveguides, but these are not the same size because of, for different frequencies. And this is actually an antenna. This one or this one here. It's not such a bad antenna. An open end of the waveguide is not such a bad antenna. The only thing we may regret, its impedance matching is not perfect. So here the reflection, this is still a discontinuity. Waveguide to free space is a discontinuity. So the impedance, the gamma absolute value is maybe perhaps 0.3. This is not perfect impedance matching. This is minus 10 dB return loss, but it's not that bad. It's a good antenna. It does not have perfect impedance matching, but we have a useful illumination efficiency of such antenna. Now, perhaps just a few words. We have a few minutes left. How do we connect the generator to a transmission line? And not like here, because here these wires are going to radiate elsewhere. So we have to think about how to illuminate our waveguide without making additional radiation. And this is a transition to a slightly larger waveguide. I intentionally brought this one with me because it's large, so you can see how it is done. This is a coaxial connector, 50 ohm coaxial connector, going to the waveguide. So this one here or this one here is the same piece. It's a larger waveguide for lower frequencies. That's all about it. And how is this thing done? If I write just the top side and the bottom side of the waveguide, so this is, I get here with a coaxial line, and this coaxial line has a capacitor here. So actually, I have a capacitance here, and I have an inductance here over this short. Okay? So the equivalent circuit now here is, if I have the 50 ohm cable here, I have a series capacitor, a parallel inductor, and I go out to the waveguide. And what's the impedance of the waveguide? It's much higher than 50 ohm. The impedance of the waveguide, here the impedance of the waveguide is in the range around Z0. And Z0 is 377 ohm. This may be even larger, maybe 500 ohm, the impedance of the waveguide. So this is actually a step-up transformer using L and C components, inductor and capacitor, to match the low impedance of the coaxial line to the high impedance of the waveguide. And the radiation comes out here. Out of the open end of the waveguide. So just to explain waveguide for all those that you didn't attend the electrodynamics course where we did these things in detail. But we saw that we can make quite a useful radiation efficiency. One thing we should care about is that we may also have higher order modes in the waveguide. So this mode we were talking here, this mode was the fundamental mode of this guide, and this was so transversal electric, because we have no longitudinal electric component, 0, 1. 0 half waves in the x direction, 1 half wave in the y direction. This was the electric field of 0, 1. Was now this 1x cosine Okay, constant cosine, constant here, constant times cosine pi over a y times e to the minus j beta z. But we have higher modes. We have the next higher mode is TE02. It is E02. It's still the direction 1x, constant, cosine, but here it will be 2 pi over a y e to the minus j beta z. And the higher mode in the other direction is TE10. This will have the electric field 10 in the direction 1y. Again a constant, again cosine, but now pi over bx e to the minus j beta z. We have higher modes in the waveguide. Let me draw the fields of these modes. Making a sketch of the fields. So I just draw 3 times the aperture. 1, 2 for the second example, and 3 for the second example. So I will just draw the electric field, not to keep things simple. So here we have just 1 half wave of the cosine. Okay. Here I will have 2 half waves of the cosine. So this direction, this one, but this direction, this one. And here the field is, of course, decaying. Decaying, here is 0, here is inverting the direction this way. And this will be in the other coordinate, so this will have the electric field in this direction, or maybe better to keep it in line with all the other explanation. And here the field is decaying towards the metal surfaces. So I have other possible solutions besides this one. This was a very simple explanation of the waveguide. I have other solutions, and there are many of them. I could just write here in place of these 2, I could just write an integer m, and maybe here also an integer n. For the modes, m is 1, 2, 3, and so on, integers, and n is also 1, 2, 3, and so on. So I have many modes and many other modes that have both x and y dependencies. So I have higher order modes. Where is the trick right now? The trick is to find the cutoff frequencies of these modes. And the cutoff frequencies here of I prefer to do this next hour. We have to do the break right now. I do this next hour. I hope it's not a problem now to break the description here, but I cannot make it in time.